Okay, so this problem here involves drums sliding on a surface. They don't really slide, they roll. Now, this is an important concept that we will discuss, and we'll probably repeat it and discuss a little more when I get one next week or the week after next, I'm sorry. But so whenever you have something that's rolling, that's being pulled, then in this case, the friction always points to the left. And that's because if you think about this, if you look at case one or case two, if I pull with P to the right, then if there's absolutely no friction whatsoever on the surface, then what would happen? It would probably just slide, wouldn't it? It would just slide along because it's going to take a certain amount of effort to roll that wheel because now the wheel's no longer a particle. It has inertia. So there has to be some minimum friction that points to the left at the bottom where it touches in order for you to actually roll. Now, it turns out that depending on how much load you apply and where you apply it, that can determine whether it rolls or if it slides. So what I mean by that is let's look at the first case, case one. So with case one, we have something like this, okay? Now, looking at the information from the diagram, we know that the outer radius, so the outer radius is 160 and the little inner radius is 80. Okay, so that would be the little inner radius right there. Now, the free body diagram. Oh, another thing is we're going to pull with a load of 20 newtons. Our radius of gyration is 120 millimeters and our mass is 5 kilograms. So of course we know that I for that is equal to mk squared or 5 times 0.12, always converting to meters squared, which gives me 0.072 kilogram meter squared. Now that won't change because the disks are the same for both case one and case two. Now, if I look at the free body diagram, what do I have? I have the load P, I have normal force, I have the weight, and I also have the friction pointing this way. So again, the friction has to be there, otherwise it would slide. In order for it to roll, there has to have some friction there. Now, don't confuse this with a wheel that is driven. So for example, on a car, let's say you have a rear-wheel drive car or an all-wheel drive car, then the wheel is driven. When a wheel is driven, not pulled like this, then the friction points to the right. And that's because the wheel is trying to push the earth away and the earth is pushing it forward. Okay, so this is a different scenario. Only occurs when you're pulling. All right. So then we can say that is equal to our I alpha MA. Okay. Now, if you know how to solve this, go ahead. I would do it and then come back. But if you're not sure, the process goes like this. And again, pause anytime. The more you do this on your own, the better you're going to be on the final. So I'm going to take a moment about C because that gets rid of the weight, the friction, and the normal force. And that's going to equal I alpha plus MA d perpendicular, which is going to be what? My 20 times 0.16, because that's the distance from P down to that point. That's the outer radius. That's all going to equal my I alpha plus 5 kilograms times, and again, I'm going to use A, assuming it's rolling, not slipping, because this only works for rolling, only, never slipping. Okay. Then I can say that, and then times 0.16 for my d perpendicular. So I solve, I get 16 radians per second squared. I plug it in up here for r 0.16. 16 times 16 is 256. So I get an acceleration of 2.56. So the acceleration is equal to this, 2.56 meters per second squared. Okay. So now the question is, does it roll? Is there enough friction to allow it to? So normal force minus mg equals 0 if I sum the forces in the y. Normal force is just mass times gravity, which is 49.05 newtons. I hate the fact that it's n and n. That's why I know for confusion. F max then is the coefficient of friction static, which was given as 0.25 times that gives us 12.263. Okay, so this is the maximum friction available. So we have to see is do we exceed that? So we go down to here and we say, let's sum the forces in the x. equal to max. And if we do that, what forces do we have? We have negative friction, again, making this way positive, right? And plus 20 equals ma. So we get 7.2 newtons. So because 7.2 is less than 12.263, we have adequate friction for it to roll. So it does. Okay, it rolls without sliding. All right. So take a second to digest that. And let's look at the next step. Now, this is case two. Now, for case two, everything's the same. The only thing different is where we apply the load. So P is down here. So now we know P being applied here. There's point C and F and the weight. And that equals I alpha plus MA. Okay. So again, we're going to do sum of the moments about C equals I alpha plus MAD. Now remember, as I derived in another video, this is the same as this because if you substitute A equals R alpha, that R and that R are the same. So you get that. So I'm going to use this time. It doesn't matter 6 of one, half dozen of the other. So we get, in this case, we have 20 is 20 times 0.08, and that's going to equal, if I use this, it's going to be 0.072 plus mr squared, which is 5 times 0.16 squared, all times alpha. Alpha this time is, so I make that clear, 8 radians per second squared. Therefore, the acceleration is equal to 8 times 0.16, which gives me 1.28 meters per second squared. And again, that's the center of mass. So the center of mass of the circle here is 1.28, is accelerate that rate. So now we have to check and see is about the friction. Now we already established that F max was 12.263. That doesn't change. So if we go ahead and sum the forces in the x equal to max, let's see what we get. Well, we have, in this case, 20, again, minus F equals 5 times 1.28. So if we do that, then we solve for F, and F is now 13.6 newtons. So what that means is that I only have 12.263 newtons of friction force, but in order for it to roll without sliding, I need 13.6. So therefore, it's going to slide. Now, the fact that it's going to slide means this and this are no longer valid because this only works if this is not sliding. So what it does is it forces us to go back and recalculate, but that's not too big a deal. I'll give you a hint. You're going to go back and you're going to sum the moments about G, the center of gravity. Okay. So go ahead and try that and see what you get. Okay, you figured it out. Good job. Or you just want to confirm that you're correct. So if I sum the moments about G equal to I alpha, again, I don't need an MAD because it's the center of gravity, then I get what? The friction kinetic now, right? Times 0.16. Now, my friction kinetic I can calculate, can't I? Because the friction kinetic is just equal to mu kinetic times n. So that's going to be what? It's going to be 0.2 times 49.05. But remember, when we did gravity in the first place, we multiplied gravity by 5. Now we're multiplied by 1/5, so we're going to get 9.81 newtons. Just a weird coincidence, not gravity. So we have this. So I guess I could rewrite this as 9.81. So 9.81 newtons, not gravity, times 0.16. That's our moment about G. And that's at the point down here. That's the only thing we have. And that equals, oh, sorry, just left something out. So It's getting late, and sorry about the mistake. So I have 9.81 times 0.16, but I also have this, right? So I have to then, and again, I'm saying 9.81 times zero point 0.6. I'm making clockwise positive as usual. So that's going to be minus 20 times zero point zero 0.08, right? Because if you think about my circle, right, I have a friction force going that way, and I have this force P going that way. And I'm taking a moment about that. Okay, so that distance there is my 0.08, and that whole distance is my 0.16. Okay, and of course that just equals 0.072 alpha, and that's I hasn't changed. Alpha is what? It turns out to be negative 0.422 radians per second squared. And that makes sense because what's going on now is the object is rolling. Instead of rolling, it's being pulled, but it's rolling backwards. So in the first case, it would roll like this, like you'd expect. In this case, because of the force and the friction, it's kind of hard to see, it's going to do, it's going to go that way, but roll that way. So case one just rolls like that. Case two, it goes, rolls backwards, but it slides. Okay. And now that we have this, we can calculate the acceleration because and even if we didn't have this, we know the acceleration is going to be what? It's going to be the sum of the forces in the x equals max. And what do we have? We have 20 minus 9.81, and this way is positive, equals 5ax. So ax is equal to 2.04. Okay. So it still accelerates to the right, except as it's accelerating, it's rolling backwards. Okay. So intuitive wise, it's not real direct. So I'd encourage you to kind of get something cylindrical like my little container of CeraVe, whatever they call this, and just use your hands to manipulate. That's the easiest way to understand it that I've found. Okay, so that is essentially most of, if not all of the things in chapter 16. And we will mop up when I'm back, but thanks for listening, and I hope you had a good week.